Hi guys, welcome back. This is part 3 of our equilibrium unit. We are sitting at the top of page 6. So right now, if you could go ahead and pull out your notes, have a writing utensil, and you might as well pull out your graphing calculator as well. Okay, let's go ahead and do a recap. At the top of page 6, I kind of bring it up again. This is not the first time you've seen this. It's talking about the size of K, our equilibrium constant. Okay. And really, you guys, it's important to recap at this point because our brain kind of goes off into math land. And it's important to kind of step back, digest everything that we've learned so far, be able to put it into context and tie things together. In just a minute, we're going to go on to studying our reaction quotient. So making sure you're solid on the previous information is going to ensure your success in the rest of this unit. Okay. All right, so let's go ahead and recap. What does the size of K mean anyway? This is on page 1 of your notes already, so we're bringing it up again because it is important that you know what this means. So there's pretty much 2 different options here. K can be greater than 1, and K rather could be less than 1. What does each one mean? Well, if K is greater than 1, then whatever chemical reaction is occurring, that the formation of the products is actually going to be favored in that particular reaction. Where if you end up doing calculations and you get a K value of less than 1, then the opposite's true, that our products going back forming to our reactants is going to be favored. So again, one more time before we move on, I want to ask you 5 things. Can you do the following 5 things? The first thing, do you know how to write the equilibrium constant expression? All right. If you're like, well, yeah, well, go back and prove it. There's some homework problems that you'll need to do this with. Number 2, can you tell me how K would change if the stoichiometric coefficients of a balanced chemical equation change? Okay. Again, if you need an example, if you go to example number 3, and that problem had multiple portions to it, so you want to look at 3C. 3C would highlight to you how to do that. Okay. You might need more practice. All right. Number 3, can you tell me how to find K for a summary equation? Summary equation also meaning, hey, I give you a set of data. Can you determine what K is? And of course, you know how to do that because you would just go and refer to exercise number 4 as a recap. So go ahead and take a look at exercise number 4 on how to calculate K for when given data. Okay, number 4, can you tell how K depends on the way equilibrium concentrations are expressed and how to convert K in terms of Kc versus Kp and the difference of the two? So right off the bat, if you're needing assistance in a review, you're going to want to refer to exercises 5 and 6. And do not forget this equation. Remember PC, politically correct, and then RT to the delta N. This equation, they love to give it on multiple choice portions. You might see it embedded within an FRQ. Bad news is they do not give you this formula. You need to memorize it, okay? And if you get enough practice, it's not necessarily hard rote memorization. It'll come easier to you. So make sure you know that, please. Last but not least, number 5, can you explain what K is actually telling us about a reaction? And that goes back to the magnitude of K. What does it mean when K is greater than 1? What does it mean when K is less than 1? So right now, if you can do these 5 things, awesome. You're ready to move forward. We're going to start talking about the reaction quotient. If you cannot do these 5 things or one of them or some of them, then it might warrant for you to go back and rewatch lectures to the necessary areas that you're needing to focus on. And remember, practice makes perfect. All right, let's go on. Let's go ahead and move on to the reaction quotient. We also call the reaction quotient Q. So you guys are actually going to be calculating Q values. Well, what's a Q value? Well, it's very much like a K value. But here's the deal. Sometimes we're going to be working problems in AP chemistry where the particular chemical reaction is not at equilibrium. If the problem that we're doing or the science that we're doing indicates that the chemical reaction is not at equilibrium, so it's not at equilibrium, then you're going to need to calculate Q, the reaction quotient. Here's the good news, you guys. The good news is that Q is calculated just like K. So I'm going to go ahead and circle for you an example here embedded in our notes. Take a look. Q is calculated just like K. Now, it was given a generic reaction here. Here's your generic reaction. That's what I like to call it. So take a look below the generic reaction. That's how we set up our reaction quotient. We set Q equal to products divided by reactants, where each one of the species within the reaction is raised to an exponent that relates to the coefficient from the balanced chemical equation. So then what's the difference between Q and K? When in the heck do we use it? What is this all about? Like I said, sometimes we'll be working problems or doing chemistry where our reaction is not necessarily at equilibrium. If the problem indicates to you that the chemical reaction is not at equilibrium, you are going to need to calculate Q first. You calculate Q just like you do K. So after you're done calculating Q, there's going to be a possibility of 3 possible scenarios to occur. One of these 3 will happen. Okay, so if you go and take a look, the first possible scenario that if you calculate Q, I'll just keep it yellow, you guys. If you calculate Q, and Q ends up being less than K, okay? So you calculate Q, you get the value, it ends up being less than K. So yes, you're going to need to be given K values in these problems as well. And when you compare the two, if Q ends up being less than K, you guys, the system is not at equilibrium. It's just not. What happens if Q is in fact less than K? Then the reactants going to the products, the reaction is going to shift right. The reaction is going to shift right to favor the products. So to recap one more time, if Q ends up being less than K, we know that the reaction that's in question is not at equilibrium, at which point, in order to get it to equilibrium, the reaction would need to shift right to favor more production of the products in order to get the chemical reaction to establish equilibrium. Now, if you end up having and doing a problem and you end up calculating Q and you compare it to the given K value and they're equal, then yes, the system is already at equilibrium. Okay, that one's an easy scenario. And again, you guys, in just a second, we're going to do an example of all of these. And the third scenario, if you're calculating Q, and again, you set it up and calculate it just like you would the equilibrium constant. But if you end up getting your value and Q ends up being greater than K, yes, that is right. Then the reaction in question is not at equilibrium. And since Q is greater than K, what needs to happen is that the reaction is going to need to shift left to favor, to favor the reactants. So it's going to shift left. In other words, the reaction is going to need to shift left in order to establish equilibrium. All right. So let's go ahead and do a couple examples in exercise 7, A, B, and C. All right. Now, remember when you're doing AP chemistry, you get just a point for simply writing the expression first. So I'm going to implore you to slow down, write out your equilibrium, your quote. In this case, you're going to be writing a reaction quotient expression, and just write it out, then plug in your numbers because you get points just for doing that. So let's make this a little bit bigger. What do we got going on here? Let's take my highlighter. All right, for the synthesis of ammonia at 500 degrees Celsius, the equilibrium constant is 6.0 times 10 to the minus 2. Predict the direction in which the system is going to need to shift in order to establish equilibrium. What did they give us here? Bam, they gave us our equilibrium constant. Look at that. K equals 6.0 times 10 to the minus 2. Okay, so right in our problem, they actually gave us K. Now, how do I know I'm going to actually be setting this problem up and calculating the reaction quotient? Well, go ahead and read the rest of the problem. You guys break this down so you can see what type of problems are being asked here. It's asking you to predict the direction in which the system's going to need to shift to reach equilibrium. If you go down to example 1, you'll see here that we have a series of substances and given concentrations. So we're going to solve for Q, compare that to K, and then that will tell us which way the reaction will need to shift in order to establish equilibrium. Now, you guys know how we make ammonia, okay? You need to know the Haber process or the Haber process. I'm not German, so I tend to say Haber. Oh, I don't speak German, rather. Anyway, it's a quick reminder. What is the Haber process? Nitrogen, hydrogen, yields ammonium. Don't forget to balance that sucker. Okay, there's the Haber process, you guys. So you need a balanced chemical equation, obviously, because when you set up the reaction quotient, you're going to need to raise each of those substances to the correct coefficient, as an exponent. Okay, one more time. Let's go ahead and get practice writing the reaction quotient expression. Make sure you write that expression out before you start plugging away, you guys. Now let's plug in our numbers. Yes, that looks right. It's a really big number, right? Really big Q number. So what do you think's going on here? Now let's go ahead and put that into scientific notation. I'll move it over 1, 2, 3, 4, 5, 6, 7. Okay, move it over 7 spots. So here's what I got. I got 1.25 times 10 to the 7. That's a really large number, like I said. So in this case, this was our Q value. In this case, Q, go ahead and take a look at the K and compare it to the K value. One more time, here's our K value. It's given to us in the problem. That's a pretty small number, K is. So in this particular case, Q is way bigger than K. So what's going to happen, you guys? Obviously, this system is not at equilibrium. The reaction is going to shift left to get to the equilibrium that we're looking for. So to establish equilibrium, we're going to need to take all those products being formed and shift it back to forming some of the reactants, okay? So in this particular case, it's going to shift left, okay? Let's do B. I'm going to let you guys, you can pause me. Again, I want you to try these problems on your own before I do them. Why don't you do B and C now that you have kind of an idea of what you need to do? So write the reaction quotient expression, plug in your values, get your answer, compare that Q value to K, and find out what is happening in the new set of concentrations given to you for B, and repeat the process for C. All right. For B, did your final answer, did you get 0.060? Well, if you go back and compare that to the K value, that looks pretty much to be the same, identical. So they are, in fact, equal to each other. So the concentrations given to us in B were, in fact, concentrations when the reaction was at equilibrium. Okay, let's go ahead and I'll just throw C down here. The answer that you should have arrived at for exercise 7C. You can easily see that Q is less than the equilibrium expression or constant K. And when that's the case, we're going to need to shift that sucker to the right. All right. In other words, we're producing a lot of our reactants aren't going anywhere. And so we need to actually produce more of the products. So in this particular case, the reaction is going to need to shift to the right in order to establish equilibrium. All right, you guys, that was page 6. I think we're going to take a break and we will pick up page 7 and a new concept. We are going to start playing around with these things called rice tables. and how we can actually do some calculations, more calculations dealing with the equilibrium constant. Okay, you guys, have a great one, and I'll see you next time.